Okay, so let me just make a brief recap of what we have done last lecture. So what we obtained is that this object, so the average of the replicated partition function, can be written in terms of an integral over a matrix, an n times n matrix. This is symmetric, so that you integrate only over one diagonal of diagonal part, and then here you have a term that is like that with S of q. This is just given by okay. And then what we have done is that we have assumed a replica symmetric form for Q. So Q was so let me write it this way. So it was 1 on the diagonal, and this is the spherical constraint, and it's Q outside the diagonal. So we have obtained the saddle point equation for Q. And then we have assumed that Q is smaller than 1. So this means that we are in the SAT phase. And then by taking the limit Q to 1, we have obtained the Unsat transition. And then what we have done is that we have shown that we can compute. So this matrix encodes the probability distribution of the overlap, the P of Q. So we have obtained a formula for this. That is, so this is just where this is the saddle point solution. And now I would like just to make a remark on this, because I think that I made some confusion last time. So this probability distribution can inherit some properties of the Hamiltonian. For example, if the Hamiltonian is symmetric, let's say, so it has some symmetry. For example, it is such that then of course this function is symmetric, okay? But this is not the general case. Okay, so now what I would like to do today is to study what happens in the Unsat phase, okay? So in particular, the P of Q is not symmetric, and in our case it's not symmetric, right? Because the Hamiltonian is not symmetric under x going to minus x. So let me say the Unsat phase. Oops. So the saddle point solution that we obtained last time was this one. Okay, and this of course depends on the temperature, right? Because you have beta here. And so what we did last time in the SAT phase was to assume that Q was smaller than 1, and then we said, okay, this term just goes to a theta function of H. Okay, now we are in the SAT phase, so there is no possibility to have unsatisfied constraints. And so what we have to do, and so in this case, Q, of course, goes to 1, and it's 1 in the unsat phase. So in this case, what we can do is to say that Q in the 0 temperature limit is 1 minus a function times T, a constant, okay? And so we can plug these ansatz inside this equation, and we can get an equation for this constant here. And the equation that you can get, I mean, this is a simple exercise, because what you have to do here, so this thing goes to 1, right? And this to Q go to 1. And then here you see that you have 1 minus Q, that is chi times T. And here you have 1 over T. So you can compute this convolution using saddle point. So I will not do it, but the resulting equation is this one. Okay, so let me just make a brief recap of the phase diagram. So at the replica symmetric level, this is sigma, this is alpha. You have a line here. This is 2, and this is the SAT phase. Okay, so this is SAT, and here you have Unsat. Okay, so if you fix sigma and alpha in some point here, you can get the value of chi from this equation. So now what we can do is to try to understand what happens if you are in this unsat phase, and then you go towards the jamming transition line. So last time we approached the jamming transition from the SAT phase in this way. So we had Q that was smaller than 1, and then we took the limit Q to 1. And now we are in the unsat phase, so Q is equal to 1, and we would like to understand how to compute this line coming from there. Okay. So the solution is quite simple, because you see, when you are here, so here you know that Q is 1 minus chi times T. And now when you cross this line, Q should become less than 1. So this means that chi, when you go towards the jamming transition, the SAT-unsat threshold should diverge. Okay? And so if you take this equation and you take the chi to infinity limit, then you should get the equation for this line. And this is quite simple, right? Because this is just 1 equal to alpha. So this will be the alpha of the jamming point at fixed sigma. And so this was exactly the same equation that we obtained last time. Okay. So there are two equivalent ways to obtain this Sat-Unsat threshold. Either you are in the Sat phase and you take the limit q to 1, or you are in the Unsat phase and you take the limit chi to infinity. Okay. Okay. Yes.
How do you know that, for instance, expansion of Q is linear in temperature? 1 minus height c. Just your experience?
Okay, so this comes actually from the way in which we got this form is so if you take, for example, harmonics of spheres, okay, so this is how this is just the vibration, the amplitude of vibration given by temperature. Okay, and that's how this is analogous, when you are in the Unsat phase, this is analogous to harmonics of spheres, and that's how you get the scaling. But the way in which you see is just plugging it inside the equation and see that it's consistent.
I understand that you get consistency.
Yeah.
But for those who are non-experienced.
No. The intuition behind that comes from glasses. Okay. Okay. Now let me just try to characterize a bit. Yes.
So I'm not too clear as to the order of the limits that you've taken here, because to get the expression in terms of the chi and, and the integral, you already taken t tends to 0.
Yes.
And then you're taking chi tends to infinity.
Yes.
But then how is that consistent with the form of the q that you've written? If you've already taken t tends to 0, q is already fixed to 1, right? And you want to change it as you cross the jamming line.
No, sorry. So here you take t going to 0, and then you get an equation for chi, right?
Yeah.
And then you take chi to infinity.
So q is actually 1 on the jamming line.
Yes, q is 1 on the is 1 in the whole Unsat phase. The problem is how it scales with t. Okay? Okay. So let me try to characterize a bit the Sat-Unsat transition. Okay, so what we said last time is that, so if you come from the Sat phase, so the entropy, that is -1, so it's the limit, the free energy, this just diverges to -infinity when you cross the jamming transition line. Another thing that you can compute is it's the ground state energy. In the Unsat phase. So of course in the Sat phase the ground state energy is 0 because the problem is Sat, right? And so it makes sense to ask what is the ground state in the Unsat phase. So what is the minimal number of constraints that are violated? So this is an easy computation, and what you get is that the ground state energy is just the limit of zero temperature of the free energy, and you can show that this is 1 over 2 chi squared, and this can be also rewritten in this way. Oops. Okay. And then the last thing that I would like to discuss is the number of constraints that are violated. Let me say this way: distribution of gaps. So what I would like to characterize is so when we introduce the model, we define the variables h mu as gaps, right? In analogy to sphere models. And what we would like to understand is what is their distribution. So we would like to define a row of h, this 1 over m. So m, of course, was the total number of patterns, which is also the total number of gaps. Okay. So what we would like to compute is the average of this object. So this is the thermal average, and of course when you go to zero temperature, then you are looking at the zero temperature phase diagram, and this is the average over the random patterns. Okay, so these functions, of course, contain the disorder. So what we would like to compute is this quantity. Okay, how do we do that? Okay, so let me take back the definition of the free energy. Okay, so F is just minus 1 over beta n. I don't write the limit, the thermodynamic limit, but of course we have to understand that we are doing everything in the thermodynamic limit. Okay, so this is and that I didn't do anything. And now I write this as okay, let me, okay, I will do every step. Right? And then I can rewrite this as right? I just used this delta function. Is it clear? Is it clear? Okay. Okay. Okay, so now let me take this functional derivative. So now I assume that v is a function that I can choose and then I can take this functional derivative. Okay, so I have to take the derivative of this with respect to v. Okay, so this is, so what do I get? So I have the derivative of the log, which just gives me the partition function, 1 over the partition function. And then I have this factor here. And then here I have minus beta m. And then I have just sorry, yes. Right? So this and this goes away. And so I just get m over n, but this is alpha, right? So I forgot the average. And then I have just, this is just the definition of the average of rho, right? So this is just rho. Okay, so if you know the free energy, and then you can take this derivative, then you have access to the distribution of gaps. Okay, now we know the expression of the free energy, so we can do this computation. Okay, so the free energy is just, I don't write the limit of small n to 0 and the thermodynamic limit, so, but this must be understood. So let me write this, okay, and so since we are plugging the replica symmetric saddle point equation, then this is just okay. So this was the starting point for the saddle point equation over Q, if you remember. So according to this, we have just to take the functional derivative with respect to V. And so let's do it. Okay, so this is alpha times rho of h, which means that rho of h is just 1 over alpha so let's compute this. So you see that this depends on V only for this term. So you have alpha that cancels out. And so this is just Okay. So of course this goes through this convolution, and so I will write it here. And so this is just gamma of q. And then I have to take the derivative, the functional derivative of this logarithm. And I hope not to make mistakes. So let me, in order to do that, let me make explicit all these convolutions. So before doing that, I will do it. So this is then you have the log. So I just have rewritten this expression in terms of Gaussian integrals, right? And now, if you take this functional derivative, then what you get is the following. So you have this external integral that stays there. As I was saying, this derivative goes through this Gaussian convolution, and so what you get is just okay. So I can write. So okay, I will just skip the details. So let me write this here. So you see that you have an external integral over z. This depends on h. Okay. So this h is is this h. Okay. So you have an external integral over z. You have h here, and then you have a normalization factor that depends on z. Okay. So you integrate over y, and this term depends on z, which is integrated here. Okay. So what you can do with this expression, but I will not do all the details, is to take so you can take the zero temperature limit and then you can ask what is the number of unsatisfied constraints in the Unsat phase. Okay, so if you take the zero temperature limit, then you would like to understand what is this number. This just so this is the the total fraction of gaps that are negative, right? Okay. And I define these contacts. Okay. So the physical intuition behind that is that if you are in the Unsat phase, if you think in terms of spheres, you are in a situation like that. So the spheres overlap. And so you are just counting how many couples of spheres are overlapping. Okay. In this case, the gap variable, which is, so if I have a sphere I here and a sphere J here, the gap variable is just their distance minus the diameter. So if this is negative, then this means that the two spheres are overlapping. So what I'm doing here is exactly the same thing. So I'm just looking at how many gaps are negative. Okay. So you can compute this through that formula, and what you get is that this is just the theta function of sigma over square root of 2. Okay. So this is at jamming, right? So in general, this is a complicated it's a function. And so what I've done here is to take the jamming limit. So I am in the Unsat phase, and then I go towards this line. And if you plot this function, what you get is something. I will plot it in a while.
And
So
H is what, just Heaviside function?
this one? No. This one is, so this theta of x is 1/2, 1 plus the error function of x. Okay?
Very interesting notation.
Yeah. So this comes from, okay. So, I mean, this was called, I think, if I'm not wrong, this is like the H function. So there are different notations. Typically, this function is a well-known function in the works by Derrida, Gardner, about more or less the same computations. So we changed the notation because for our spheres, this was the function
So
that
you
was
made
used.
a tag symbol for that, you know?
No, it's just a big theta. Okay, so of course here in the Sat phase, z is equal to 0, right? Because here you can solve the constraint satisfaction problem, and so here is z is equal to 0, and here z is greater than 0. And when you go towards this line, you get that the limit. So let me fix sigma, okay, and then I do the limit of sigma going to sigma, alpha. No, plus, okay, of z of sigma and alpha. And this is just this, okay. Okay, so therefore what happens is that when you cross the jamming transition, you have a jump in the number of contacts, okay. Okay, so the interesting thing to look at actually is m times z. So m times z is really the total number of constraints that are unsatisfied. And what we would like to do is to compare this with n, okay? So you could have three cases. So this could be greater than n, and I will call this situation hyperstatic. It could be equal to n, and I will call this isostatic, or less than n, and I will call this hypostatic. I think I should write it like this. Okay. So you can define C, that is alpha times Z, and this is greater than 1 if you are hyperstatic, equal to 1 if you are isostatic, or less than 1 if you are hypostatic. Okay. And so you can plot this, so we call this isostaticity index. And you can plot it along this jamming line. And what you get is the following. So this is C as a function of sigma. So this is 1. So it's something like that. And then in principle here it goes up. Okay. I don't want to write this because I will tell you why I don't want to write this. So here it's hypostatic. And here it's isostatic. Exactly at this point. Okay. So let me. Okay. So in principle, if you use the formula that this formula that is valid if you assume the replica symmetric solution, you get that this line goes up. So in principle, here it's hyperstatic. But what I will show you now is that this part of the phase diagram, in this part of the phase diagram, this Sat-Unsat transition line is in a region where actually you cannot use the replica symmetric solution. Okay. So for sigma negative, the replica symmetric ansatz is unstable. Okay. So before doing that, I would like just to come back to spheres, because we discussed a bit the properties of the jamming transition for our spheres in the first lecture. So suppose that you take a packing of our spheres. Okay. So this is jammed, so spheres do not overlap. And I just make a contact network. Okay, so I'm not writing an amorphous packing. This is a lattice packing, but okay. Let me do it more randomly. I don't know, like that. Okay. So in d dimensions, so the total number of degrees of freedom is n times d. So this is number okay. So this n is the total number of spheres that I have in the packing. And now the total number of constraints, so the total number of contacts that I have is, so let me call Z is the degree, the average degree of the contact network. So it tells you a typical spheres with how many spheres it is in contact. Okay. So the total number of constraints here is z times n divided by 2, right? So this is the number of constraints. The number of contacts, okay, or contacts. Okay, so in this system, in order to have a stable configuration, what you have to do is that you should have that the number of constraints should be at least greater or equal with respect to the number of degrees of freedom. So what you would like to have is that z times n divided by 2 should be greater or equal than n times d, right? And so this gives you that z should be greater or equal than 2d. Okay.
So stable meaning?
Meaning that this is blocked, this is mechanically stable. If you make just one move, everything should move. Or if you have boundaries, everything is blocked. Okay. So this is the Maxwell argument. It's due to Maxwell. And it happens that if you have z equal to 2d, then you have exactly the same condition here. So you have the number of degrees of freedom that is equal to the number of constraints. And so this is the isostatic So this means that the packing, if it has an average, if the contact network has an average degree that is equal to 2d, it means that the packing is isostatic, right? So it turns out that if you do like numerical simulations of our spheres and you produce amorphous packings, you always find that this thing is satisfied. Okay, so amorphous packings are found to be isostatic. And it's very hard. I mean, if you have a very big system, you will never find hyperstatic packings. Okay, this is a, let's say, an experimental observation. Okay, so amorphous packings are isostatic. Okay.
Pierfrancesco only for frictionless packing.
Sorry?
So only for.
Yes, only for frictionless spheres. If you have friction, then it's more complicated. Yes. Thanks. Okay.
But somehow, for instance, if you would have, I don't know, of course, little known about the most dense packet in large dimension, it would be z probably would be exponential.
Yes. This is for amorphous.
Yeah, no.
Maybe they are not optimal in the sense of best.
No, of course. It's funny, so big gap.
Yes, it's a big gap. Okay. Okay. So you see that here you are in a kind of marginal situation in the sense that if you just remove one contact, okay. So for example, you just put a dipolar force between two spheres, then I mean you destabilize the packing, and actually the packing starts to flow. So that's why this means that packings, amorphous packings, are marginally stable. Because this condition tells you that they are on the verge of an instability point, right? Okay. So what we have seen here is that in this case, when replica symmetry is unbroken, so the jamming transition line is hypostatic, okay? And only when you go at sigma equal to 0, they become isostatic. And what I will show you in the next lectures is that actually here, this line is like that. Okay. So for sigma negative, the jamming transition line is such that all the solutions that you find to the CSP at the jamming transition line are isostatic. Okay. So when the constraint satisfaction problem is non-convex, because we are in the here we are in the non-convex region, then the jamming transition line is isostatic, okay, like in our spheres. Okay. So if you want to have there is I think a beautiful review by Mueller and Viart on this. It's on annual review of condensed matter. And I think it's 2015. Okay. Okay. Okay, so what I would like to start to do now is to study the stability of the replica symmetric solution. Okay, so let me rewrite the S of Q. This is 1/2. So we have found a solution for Q that is replica symmetric. And now let me expand this function around this saddle point. So I will have this is the replica symmetric saddle point solution. And then in principle here I have plus 1/2. So I just say that Q, so let me call this Q star. QAB is Q star plus some fluctuation. Okay, so of course there is no linear term because Q star is a saddle point solution for S. And here I have the sum over A less than B and C less than D just because I'm only considering fluctuations that are matrices which are symmetric. Okay, so I can rewrite this term symmetrizing everything. So I can rewrite this as 1/8 A different from B from D. So this operator here is obtained from this with a symmetrization, okay? So I just symmetrized this operator, okay? And this operator is what? So this MAB CD is just computed at the saddle point solution. Okay, so remember that we had to compute this. Oops. And so what we need to do is to check that if we compute the saddle point, and this saddle point is given by Q star, then this quadratic form should be semi-definite negative, right? Because it should be a maximum here. And so what we would like to do is to compute the eigenvalues of this operator here. Okay, let me try to do it. So the first thing is to work with the symmetrized operator. So what you can show, I mean, it's quite, with a bit, let's say, with a bit of reflection, you can show that this operator, computed on a replica symmetric saddle point solution, has this general form. Okay, and the main reason is that if you take A, B, C, and D, you can have these situations. So either you have, so you have to remember that here A is different from B, and C is different from D, of course, because this follows from this, right? You are just perturbing the off-diagonal elements of the matrix. So you can have three possible situations. Either A is equal to C and B is equal to D, or vice versa, A is equal to D and B is equal to C. So this is case one. Then you have A is equal to C, and then B is different from D. Okay. And the third case is that A is different from C and D, and B is different from C and D. Okay, and this means that you can arrange this in this form with three coefficients that just depend on this on these three things. Okay, so this way, so this computation was started in the context of the Sherrington-Kirkpatrick model by De Almeida and Taules. So So this is the Sherrington-Kirkpatrick model, that is a spin glass model. So it was done by De Almeida and Taules. And we will redo it in this case. So how do we compute this? So the strategy is quite simple. So given this, what you can try to do is just to compute the following three objects. So you compute, so you first compute the derivatives with respect to 1, 2, and 1, 2. So you say that A and C are equal to 1, and B and D are equal to 2, and you are just realizing this situation. Then you have M 1, 2, 1, 3. And you have this situation, and then you can compute M1, 2, 3, 4. Right?
Yes.
And now once you have this, you just plug this into that, and then you obtain the expressions in terms of M1, M2, M3. Okay? So you have, so let me call this T, so that I don't mismatch anything. So you have T12 is just M2 Okay, and so you can just invert this in order to get m1 that is equal to 2 times okay. So we need just to compute these terms that are just derivatives of S of Q. Okay. So maybe it's better if we make a break now, and then I will continue later. Okay. So I will do I will not do all the computation. I will just give the ideas and basically the technical steps. So what you do is first you write S of Q. So I call this an entropic term, and then you have an interaction term. So this is 1/2 log that of Q, and this is the other one. So it's alpha log the exponential of things. Okay, so I will sketch the computation of the derivative of this in two parts. So I will just do the derivative of this term and then of this one. Okay, so let me consider this entropic term. So as I told you, we want to compute these objects. Let me call this TE. Okay. Now, if you do it, then what you get is just minus. So let me write it this way. Wait. It's 1, 1, 2, 2. You have just to take the derivative of the log of the determinant with respect to this. So the first derivative, so if you do, let me write an explicit formula. So if you have a matrix, log that of A, then if I'm not wrong, so the first derivative is just sorry, in principle it's BA, and then if you take the derivative of this is so you have to take this derivative, so you have a minus sign, and then you have A minus 1 AC A minus 1 dB. I think this is correct. And here, these terms just arise because this matrix is symmetric in the end. So this expression is in terms of a symmetric function, and so you have to take care of the derivatives with respect to 1, 2, and 2, 1. Okay. So using this, you can get all the terms. I will write them here. So you have T 1, 2, 1, 3. And this is simple because it's Q minus 1, 1, 1, 2, 3. 1, 3, 2, 1, 2, 3, 1, 2, 1, 3. Hope it's okay. And then you have the last one, that is one, 3, 2, 4 plus 1, 4, 2, 3. Okay, and you have to compute this at the saddle point, right? So q minus 1 should be the inverse function of the replica symmetric matrix. So if you have QAB, that is 1 minus q delta AB plus q, then q minus 1 AB. So for n to 0, this is just 1 over 1 minus q delta AB minus q 1 minus q squared. Okay, so I mean it's an exercise. You can just do and you can just say you can just plug these two expressions inside this, and if you take, of course, this is true in the limit of n going to 0. Okay. So if you plug this expression into this, you can compute all the terms. Okay. So this is a kind of simple thing. Now let me consider the other term, which is a bit more complicated. So let me consider the other term. So let me first of all compute this. So let me consider the Sat phase. So in this case, I can use this, right? And this is the EV side function. Okay. So what we have to do here is just to so we have alpha okay, let me write theta. So you see that when you compute these derivatives, you have just differentials operators that go down. And so if you do it, what you get is just, so I will write things with a kind of notation that is so what this means, it's just and at the denominator you have exactly the same thing with this going to 1. Okay. Is it clear? Okay. So Okay, so let me compute first the normalization. So this is just e to the so I plug the replica symmetric ansatz here, and so this is just I'm just doing the same steps that I've done the last lecture. Okay, and so this is just okay, and so if I take the n to 0 limit, I just get 1. Okay, and now let me consider the numerator. So, for example, let me compute this one. Okay, so what I need to compute is then I have d1 squared theta. Let me write this way. Okay. This is from 3 to n, right? Because I've already taken the first two. And now I'm computing everything at 0. Okay, it's the same. Okay, so now I use exactly the same thing. So I rewrite this operator with the replica symmetric form of Q. And so, of course, okay, so what I get is just, I write and then I explain. And then I have here, sorry, from 3 to n. Okay. So what I did is just that, okay, let me, so this is of course right? So I can use this term and apply it to this. And of course, this is decoupled, right? Because it's a free sum over L. And so you have the term with 1 and 2 that applies to this function, and it commutes with these derivatives. Okay, and so I get just this convolution. And then when I apply this to this term, I have just this. Okay, I just use that this differential operator commutes with these operators here. Okay, and so what we get is just okay. So So this makes a convolution. And then I have, of course, these two becomes, since I'm computing everything in 0, this is just squared, and this square comes from the fact that these two are the same, and then I have to the n minus 2. Okay, because these are n, but here it's from 3 to n. Okay, so it's n minus 2. Okay, and so when n goes to 0, what we have is just okay. Okay, so you can define, so let me define this function. I'll do it here. Oops. For the moment, I will not tell you what this one means, but this will be clear later. Maybe this one, this lecture, or the following one. So I define this function as okay. So then what you can do, so you see that this function is just the function that appears here. Okay. And so what you can show, just doing exactly this computation for all the derivatives, you can show that 1, 2, 1, 2 is just alpha times, so I will tell you what this average means. So this is exactly what we computed right now, right? So it's the second derivative with respect to h divided by the same function, squared. Okay. And so this average is just this Gaussian integral here. And then you have the other term that is exactly the same. I mean, it's close to that. It's squared. And then you can do exactly the same computation for all the terms. So 1, 2, 1, 3. And you have an expression that should be. So I indicate with this the derivative with respect to h. Sorry, I didn't tell you. So the second g prime. So here is g prime square cube minus the same thing here. And then you have the same expression. I mean, I will not write it, but you can. I will write it in the notes. So once you do that, you can compute all the elements of the stability matrix. Okay. And then starting from that, you can compute the eigenvalues and eigenvectors. And you can look for their stability. So I will not describe the full, the diagonalization of the stability operator, but I will tell you just the result. So the result is that if you look to the eigenvectors, there is one particular eigenvector that is called the replicon. And this is an eigenvector of this form. So you create a fluctuation, delta QAB, that is such that the sum over C of for different, so sum of B, which of course should be different from A, so this is a constraint on the form of this matrix, okay, and this defines a subspace in the space of the fluctuations delta Q, okay. So you can show that the matrices of this form are eigenvectors of the stability operator, okay, and the eigenvalue is proportional. I mean, now I'm not sure about the. Okay, but this eigenvalue is minus 1 over 1 minus Q. It's given by this. Okay, so we will compute this expression in a easier way, maybe next lecture. But the important thing is that if you compute this on the replica symmetric solution, you discover that this eigenvalue becomes unstable at some point. And in particular, if you look to the phase diagram, so this is the Unsat line. So here is Unsat. This is Sat. And there is a line here. So this is the replica symmetric jamming line, or the Unsat threshold. And this is the line where this eigenvalue becomes unstable. Okay. So this is called that from De Almeida and Taule's instability. Okay, so it's where this thing becomes unstable. Okay, so the first thing that you see is that so for sigma that is negative, the jamming line, the Unsat threshold, lies inside a region of the phase diagram where the replica symmetric solution is unstable. So the way in which you computed this line is wrong, okay, because we computed it using the replica symmetric solution, okay. And so the question is how we can compute the properties of the phase diagram here, what happens here, okay. So what happens here is at least clear from this point of view, in the sense that you see that this matrix, the form of the eigenvector here is just telling you that the replica symmetric solution is no more a good one, in the sense that you have to break replica symmetry. Because in order to have matrices that go in the direction of this eigenvector, you have to break the replica symmetry. Okay. So already this eigenvector is telling you that replica symmetry is broken. Okay. Because you want this not to be of the form of a replica symmetric matrix. Okay. And so that now the main point is how to break it. What is the correct scheme in which we need to find the saddle point solution? Okay. So I will not do the computation in the Unsat phase. You can do exactly the same thing in the Unsat phase, and you discover that here there is a line that separates a replica symmetric saddle point stable phase, sorry, from a RSB broken phase. So in this region here, replica symmetry is broken. Okay. And now the problem is how to compute the properties of the phase diagram here. Okay. So all these things have have been discovered not in this model. So the fact that you could have replica symmetry breaking was discovered by de Almeida and Taules in the context of the Sherrington-Kirkpatrick model, and there were a lot of attempts to find a saddle point solution that was consistent, and then finally the correct, that we know that now that it's correct, at least in that model from a mathematical point of view, the correct solution was found by Parisi, and I will try to describe it today and in the next lecture. So in the context of the Sherrington-Kirkpatrick model, there is a spin glass. The Parisi scheme of replica symmetry breaking is the correct one. So it's proven that it gives the right free energy. So in this context, things are more under investigation. So it's not clear if one can generalize the proof to this case. Okay, so what is replica symmetry breaking scheme that was introduced by Parisi? So okay, so the plan for this will be the following. I will first introduce the Parisi scheme of replica symmetry breaking. Then I will discuss the physical implications. And then I will show you how to perform computation. Okay. Okay, so let me start from this. So let me consider again the replica symmetric ansatz. So we have QAB, so RS. We have QAB. And if you look to the matrix, then this is 1 on the diagonal. This is the spherical constraint. And you have Q outside. So replica symmetry breaking is constructed in a iterative way. So you first do, let me do the first one-step replica symmetry breaking. So according to this ansatz, that for the moment it's just an ansatz on the form of the matrix, what you do is that you take this matrix, okay, so you have 1 on the diagonal. So this is an n, small n times small n matrix. And now you just divide it in diagonal blocks here. Okay. Each block has sides m0. Okay. And here you put q0 and here q1. So you have enlarged the space of parameters that are needed in order to parameterize the matrix. So in the replica symmetric form, you have just one parameter, this q. And here you have q0, q1, and m0. Okay. Okay, so this is the 1 RSB ansatz. So of course, here you have n over m0 groups of replicas. Okay. So you see that you have broken replica symmetry in the sense that this group of replicas are closer. Okay. So if you take the overlap between two replicas inside the same block, this is high, And if you take the overlap between two replicas in two different blocks, for example, this one and this one, this will be, we will see that is lower. Okay, so typically Q1 will be greater than Q0. And then I will tell you why this is the case. Okay, so this is the one RSB.
Sorry, I do not understand what you put in the non-diagonal part of the other blocks. Which Q you
Here?
No, the other block you.
Sorry.
One.
It's the same for all the diagonal blocks. Okay. Okay. So this is one-step replica symmetry breaking. And now let me go on. So in order to go from one, so now what I will do, I will go from one step replica symmetry breaking to two. So what you do is that you take all the diagonal blocks, okay? So let me just make a zoom on one of them, but you do the same procedure for all of them. So let's make a zoom on this one. So this is an M, so let me write it bigger. This is an M0 times M0 matrix. Of course, it has 1 on the diagonal. And at the 1 RSB step, it has Q1 outside, right? So within this block, you have a kind of replica symmetric solution within this block. Okay. Now what you do is that within this block you repeat exactly the same procedure that we have done here. So in order to obtain the two RSB ansatz, what you do is that you introduce diagonal blocks of sides M1. And here you put Q2. Okay. So you see that this gives you an algorithm to construct in general KRSB ansatz. So the algorithm is that you start from K minus 1 RSB. Then you take the innermost blocks, okay? And then you introduce new diagonal blocks of sides M K minus 1. You see, for example, here for the 2 RSB solution, we have M1. So here it's 1, and this is for a 2 RSB solution. So in general, for a K RSB solution, I will call the block sides, the innermost block sides MK minus 1. And you introduce QK. Okay, for example, here for 2 RSB, QK is Q2. Okay, so this is an algorithm. Okay, it's just an ansatz for the matrix QAB. Okay, and of course this ansatz depends on a lot of parameters because you have all the Q's and M's. Okay. Okay. So up to now, of course, we have n replicas. Okay. Then you have here you have blocks of sides M0, which is smaller than n, which is M0, of course, is larger than M1, which is larger than mk minus 1. And mk minus 1 is greater than 1, right? Because this should be greater than 1. 1 is just a diagonal. Okay? And now we want to take the n to the 0 limit. And now the black magic is that in order to take the n to the 0 limit, you have just to reverse these inequalities. So you have n okay. So once you have this, you can represent all the q's inside a function. So you have q of x is a function of x. So x goes from n to 1. So from n to 1. And here I put m0. This is m1. This is mk minus 2. Sorry, this is mk minus 1. And this 1 will be called also mk. So I will use the notation in which mk is equal to 1. And now I can write this function like that. So I have q0. This will be q1. And then up to here, which is qk. Okay, so this way I go from a matrix representation to a kind of function, to a function, okay? So if, for example, if I take a replica symmetric solution, the replica symmetric solution is simple. So the RS case is just a constant. So I have n1, and this is just a constant. Okay? And you see that this is quite interesting because now you can consider to take the limit in which the number of replica symmetry breaking steps goes to infinity. And in this case here you have a stepwise function, but then the points where these jumps become dense in this interval. And so you go from a stepwise function to a continuous function. Is it clear? Yes.
At the beginning, you also have kind of dividing relation between from the
Yes.
0 should divide n. Do you still keep it when you do the next step?
No, because it doesn't make sense. Because the relations are just for integers. And now I'm taking the n to the 0 limit. So this just becomes real numbers in the interval n1. Okay?
So you had all the interval between 0 and 1.
Yes, I have just all these small intervals. And the physical meaning in terms of dimensions of submatrices is completely lost. Okay, it's there only if n is larger than 1. Okay. Okay, so once you do the oops. Yes?
Can you comment a little bit? So when you take the n to 0 limit,
Yes.
why do you invert the sign of this equality? I mean, I understand that n must be less than 1, but why the others must have that order?
Well, because, I mean, if you want, I mean, it's just that, I mean, you send n to 0 and this cannot be satisfied anymore.
Yeah,
So the only way, no, I agree with you, it's kind of black magic.
Yeah, but I mean, you could put them in every order.
Well, and then you call it them any, I mean, I don't know. It's in which order you want to put them?
No, I mean, why do you have to say that n0 is less than n1 and n1 is less than n2? I mean, you just have, if you take n to 0, you just have that n must be less than 1 for sure.
Yes.
And then, well, and then all the m must be.
You want to keep an order.
I mean,
I mean, the reason is that you want to keep an order here. Here you have a kind of ordered structure, and then you want just to keep the order some kind of order. Okay.
Yeah.
And of course this reflects a kind of nested structure, right?
Yes, yes.
And here you have a nested structure too, you see? Because if this is something like that, then you are respecting kind of the nested structure that you had before.
Okay.
But it's true that it's strange, no? It's not.
Yeah,
Okay, so if you take the limit in which k goes to infinity, then you can have a function q of x that will be something like that, typically. Okay. So I'm writing an increasing function, of course. So the assumption is that qi is always greater or equal, let's say, I minus 1. And this just gives you an increasing function q of x. Okay. So you go from the set of qk to a function q of x. And now I just introduced the annotation. So we started from a matrix Q, and then I say that within this full RSB parametrization, this is parameterized by the diagonal part that here is 1, and the off diagonal part that is given by a function. Okay. Okay, maybe in the last few minutes, I just try to explain what is the physical meaning of this. Okay, so let me take back the probability distribution of the overlap. Okay, so we showed that if we plug a replica symmetric ansatz for this, then we have just that the p of q is a delta function of q minus the saddle point of the replica symmetric solution. Now let me consider what happens if I consider a 1 RSB ansatz. Okay. So let me consider one RSB case. So this is RS. Let me consider one RSB. So the P of Q okay, now what to now in this case I have a matrix that is like this, no? So it's here I have Q1, here Q0. On the diagonal I have 1, but the diagonal is completely irrelevant. And this is M0, okay? And then I have n over M0 blocks, okay? So let me compute this, assuming this form for the matrix QAB. So what is this? So you see that I have to sum all the elements of the diagonal part of this matrix. Okay. So let me start from this. So for each block, I have just M0 times M0 minus 1 divided by 2. For this block, this sum, so if this sum runs only on the indices of this block, I have just this, right? Because all the elements here are equal to Q1, and I have M0 times M0 minus 1 divided by 2 elements, right? It's just the upper part, let's say, right? And then I have N over M0 blocks, right? And then I want to sum the terms that appear here. And this is what? This is just 1/2. I have to take n squared minus m0 squared. So I take the full matrix, I divide it by 2, and I subtract the diagonal part that are given by m0 times n over m0. Right? Okay, so let me take this limit. So these two go away, then this one go away with this one. Then I have this, let's simplify with this, this, and this. And if I take, so then I have these two that goes away with this. And then I have, so here I have a minus sign because it's n minus 1. And so you have just to revert the sign of all these expressions. So you have m0 times delta no, sorry, is it sorry, let me see. Yeah, sorry. 1 minus m0 q0 plus m0 is it oh, no, I made some mistake, sorry. Right? So you have this,
Yes.
which is this, and then this goes to 0, and then I have a reverse sign here. So it's m0 times delta of q minus q0. This is not there, right? Okay, so this is interesting because, so we would like to have a probability distribution, and so you see that m0 should be less than 1, right? And what this m0 is just the weight is connected to the weight of these two delta functions. So what this is telling you is that if you take two replicas, okay, you could have two situations. Either their overlap is Q0 with probability m0, or it's Q1 with probability 1 minus m0. Okay, so this means that if you consider the space of solutions here, this is something like that. So you have the full the whole space. So if I pick two solutions that are inside the same cluster, then their overlap will be Q1. But if I pick one solution here and another one there, then their distance will be Q0. Okay? So there is some kind of physical interpretation of this form. Okay? And now what we can do is just to do the same thing in the case in which we consider a full RSB ansatz. And let me do it. It's not difficult. So just before going there, so you can represent this with a tree. So here you have these clusters, okay, and the typical overlap between two solutions inside the same cluster is Q1. But if I take one configuration, one solution here and one solution there, then their typical overlap will be Q0. Okay. So now let me try to do the KRSB thing, and then I will stop. Okay, so if you take the KRSB level, what you have is a similar structure, but then here you have subclusters at any level, okay, up to the K level. So you have Q0, then you have Q1, then you have Q2. And then up to the end where you have QK. Okay. So this structure is called ultrametric. And you can find a lot of more in the book by Mézard, Parisi, and Virasoro. Okay. And now let me assume that K goes to infinity, and let me compute the P of Q. Okay. So maybe I'll do it there. So again, we start from the usual formula. Now what I do is that, okay. So how do I do? So let me rewrite this. Okay, I can rewrite this way. Okay, and now let me. Okay, I hope I will not make errors. Okay, so this is n. So for each line, you see that for each line, so for each A, and you have n of them, the result, you are just summing a matrix that is delta Q minus QAB. So you can imagine that this is a matrix and the elements are just deltas, right? So for each line, you are just summing all the elements in a line except for the diagonal, right? And so what you have here is just the sum from okay, do it this way. Okay, it's from I to 0 to k. Then I have mi minus 1 minus mi qi, sorry. Okay, and now this is just minus. So in the fuller, when k goes to infinity, so this mi minus 1 minus mi is minus, let's say, a differential, the x, so they are very close, and so you can. So this is just given by. So you have these two go away. This one is a minus sign, and here you have a minus sign that comes from this. So you have just the limit. So this sum becomes an integral. Okay, so you have minus sign, so it's just the integral, the y from from n to 1. Okay. And now if I just introduce the inverse function of q, so if I have q of x, then this is just okay. And therefore so if you start from a q of x that is like that, then what you get is that the p of q, let me call this q0 and this q in A, you will have two Dirac delta functions here that are due to, for example, to two plateaux. I mean, the fact that you have two plateaux here, it's something that arises when you solve the equations. So it's a kind of typical situation. That's why I wrote here. But of course, for the moment, we don't have the right to write two things like that. But I will do it just because this is the typical situation. So you have two Dirac delta functions here that are connected to this, and then you have something like that. Okay. So you have a continuous probability distribution to get overlaps in this range. Okay. So this means that typically, if you take two solutions, if the space of solution is of this kind, if you have a full replica symmetry solution, then the probability that two typical solutions, the average probability that two typical solutions are at distance q is given by this. Okay. And I stop here. Okay.